Oh,
All right.
Actually, like 180.
So here's what we've got right now. So this is the same cell that we had yesterday. We had copper, the zinc. We figured out what was being reduced and what was being oxidized. Now, what we're going to get into now is what's going to happen when you don't have standard conditions. Okay? So standard conditions in terms of solutions. Everything is 1 molar. Temperature is technically 25 degrees Celsius, which is a little bit on the warm side because right now we're at about 21 degrees Celsius. Technically, it needs to be about 25, but usually the temperature variation isn't that much. What we're going to focus on is variations on the concentrations. So, when you calculate this value E naught, okay, so anything that has a naught value, that indicates that it's under standard conditions. So, who's got the reduction chart? Okay, so what's the standard reduction potential for zinc turning into zinc ions?
0.76.
And that's the way it's written? Or is that already said?
It's written the opposite way.
So it's
negative.
0.76. Okay, cool. Now, what's the value for Cu2 plus turning into copper?
0.34.
0.34. And that's as good as written. So the copper is going to go in this direction. That's going to get reduced. The zinc's going to get flipped because that's better off giving up the electrons. So if I add these together, I get 0, 0, or 0, 0, 1, 1.10 volts. So this 1.10 volts is the E naught value. So in theory, that's what the voltmeter should read. Now, invariably what happens, the voltmeter always reads a little bit less than that. And typically it reads less than that because there's some resistance within the wires, and that's usually the biggest downfall to this. Okay? So like right now we're at
Doesn't the copper you touch the blue sir?
yeah.
What are you doing, Michael?
Hey, why are you playing
nothing
Jenga,
happened.
dude?
Hey, nothing happened. Nothing happened. Nothing
Okay.
happened.
So we're reading right now 0.873. It should read 1.10. There's some resistance. We're down a little bit. So, but the E naught value is like this theoretical.
Big Mike.
I didn't spill any. I was just telling Colin that was that this is phenolphthalic.
He had
That
his
he
glasses
shouldn't spill any phenol.
Okay. So, in this equation, this is what's known as the Nernst equation. It's E naught, which in this case is going to be 1.10 volts. That's the theoretical value. I'll explain later where 0.0592 comes from. It's just a number. Accept it. N is the number of electrons from the balanced equation. Now, in this situation, because this is given up 2 electrons, that's taken into electrons, N is just going to have a value of 2. Now, this is where we revisit this concept of Q versus K, like KSP and QSP. Anytime you see an uppercase value of K, what do you have? Equilibrium. Lower, when you have Q, that's like a snapshot. Now, Q can equal K if the system happens to be in equilibrium. So this value of Q, just like you did with KSP, it was products over reactants. It's the same idea. So how you're going to calculate this value of Q, and when you look at this overall reaction, because here's this overall reaction that's taking place. Zinc, you have Cu2 plus, it's taking in electrons, you're making copper, and you're increasing the concentration of your zinc ion. I don't worry about the zinc and the copper because I can't talk about the concentrations of those because they're chunks of metal. I can talk about the ions. Now, So in this situation, how I'm going to calculate Q is the zinc ions concentration divided by the copper ion. Now, conveniently, if I'm under standard conditions, what's going to be the concentration of both of those? 1. What's the log of 1?
0.
So E is going to equal E naught, as long as it's under 1 molar concentration. Okay? Now, here's what you have to watch. In this case, it isn't. But if there had been like a 2 in front of that, let's just say, if there had been a 2 in front of that, what would we do with the zinc ion concentration?
Square it.
You'd square it. Because this is how KSP and QSP are related to the same concept. So if there's any coefficients in front of the balanced equation, that tells you if there was a 2 there, that would get squared. If there was a 3 in front of the copper, that would get cubed. Okay? So be careful of that. We don't have to worry about it in this situation. Now, here's what I'm going to do. So right now, we're at like 0.846. So what I'm going to do is I'm going to greatly dilute the copper solution by adding a whole bunch of water.
Whoa.
Okay? So I added a whole bunch of water. Now, I'm going to put that back in. So let's look at this. So, mathematically, what's going to happen to my zinc ion concentration?
Decrease.
That's still going to be the same. That's still going to be at 1. But what's going to happen to my copper ion concentration? This isn't the number of copper ions.
Down.
This is the concentration.
Down.
So this is going to go from 1 all the way down to maybe 0.001. Okay? Now, here's what's going to be important. Mathematically, if the copper concentration goes down,
Q gets bigger.
Q gets
Bigger.
bigger. Now, who's got the calculator? Okay. Take 1 divided by 0.001. Take the log of that. What do you get?
Oh, I just fucking
4.7.
well, I was just filling out.
I get it.
working on it.
All I want is the log of Q.
3.
3?
What?
Is it really 3?
Say that again.
That makes sense.
Hey Siri. My bad. Sorry.
Okay. Now, here's what's important. I'm going to have E naught, which is 1.10. The log, when I'm taking the log of Q, and I'm taking 1 and dividing it by 0.001. So this is going to be a really big number. Okay? Q is going to get really, really big because I'm taking 1 and I'm dividing it by 0.001. Which means I'm only taking the log of a big number. Log of a big number is a positive number, right? So I'm going to take 0.0592. Now, actually do this math. Take 0.0592, divide that by 2, and the reason I use 2 is because there's 2 electrons, okay? And this is from the balanced equation. If it had been like 3 and 2, I would have used 6. So this number comes from when you add the 2 half reactions together, okay? So that's that least common multiple. Electrons cancel
But
out.
3 plus 2 is 5. Right.
So take 0.0592, divide it by 2, times 3, and then subtract that from 1.10. What do you get?
I just gotta guess.
1.0112.
1 point what?
0.111.
So 1.01 volts. So notice that my voltage dropped. Now, if I come back over here and look at what we had, and if I put this in here, okay, I was at like 0.837, and now I'm down to like 0.778. Okay, so that dropped. Now there's 2 ways. Step away from the room.
Students are pictures.
Best and brightest.
I'm gonna pop your head like that.
Okay, where's the
Okay. So there's 2 ways you can understand this. One is a mathematical way. So when I drop the concentration of the copper, mathematically, because this is getting smaller, Q is getting
Big.
bigger. So I'm taking the log of a big number, which is a positive value, which means this gets subtracted. So if you're into math, you can explain this, mathematically. Cool. Now, if you want a socioeconomic way to look at this, the copper ions are pulling the electrons. So by decreasing the concentration over here, if you view this from a party perspective, when I decrease this concentration, there's fewer copper ions per unit of volume asking the electrons to come over. So they're going, I'm really not feeling it, okay? Because there's a smaller number of copper ions per unit of volume, because this is concentration, okay? So it's become more dilute. So instead of having all the copper ions in one place, and everybody's like feeding off each other, go, hey, let's everybody send out the same text message. Let's get everybody over here. Now you have the same number of people sending out the text message, but they're more dilute, okay? Goes down. Now, what would happen if I reverse this? What if I kept a high concentration of copper ions, but I decreased the concentration of my zinc ions?
You're going to divide by a bigger number, Q gets smaller, final answer.
Q would get smaller. That would mean E would get, so there's an inverse relationship. As Q goes up, E goes down. Okay? Now, keep in mind what's happening here. You're making zinc ions. If I had a really, really high concentration of zinc ions and a really, really low concentration of copper, E would get way out of whack because of the fact that you're going, wow, this is really crowded and there's not many people over there. Now, you can do one other thing. So I'm going to get rid of this with my copper ions. Do this. This is what's known as a concentration cell. So here's what I want you to think through. I'm going to have a really low, I'm going to have like a 1 molar solution over here with copper. And then I'm going to have a dilute concentration cell over here. So I've got a dilute concentration and a concentrated one. Mother Nature's not digging it. What does Mother Nature want to do with a high concentration?
Equilibrium. So
Make it go.
Down.
Well, what does it want low concentration to do?
Increase.
Go up.
To go to equilibrium.
So if that's the case, if this is the low concentration one, okay, so if this is my small concentration of copper, Mother Nature wants to boost that. So what's she going to do?
Take it from the other port.
So electrons are going to flow over here. So if this is the low side, Mother Nature wants to make more copper, right? She wants to make more copper ions. So what's she going to do?
Steal it
Going to steal what?
from the other side.
Yeah. So if this is the high concentration of copper ions, Mother Nature wants that one to go
Down.
down. So the electrons, this concentration is going to go down, right? So electrons are going to flow which way?
From that way to that.
So it's going to flow from
That to that.
high low?
Yep.
Okay, keep that in mind. This is what's known as concentration zone. Let's get back because you all have to go.